let's get some practice identifying the reagents necessary to carry out certain transformations. And so we might see a question on the exam that has a box right here, and we're asked to fill this in for 4 points on the exam. And you can contrast those with questions on the exam that might have a box right here, or just a blank space, and they say fill in the major product of this reaction. So let's think about these reactions in terms of what reagents do we need to achieve the product. And we can evaluate them in terms of the 4 major components of substitution reactions. We could talk about the substrate. We could talk about the leaving group, evaluate that. We could talk about the nucleophile, or what we might need for a nucleophile. And we can look at the solvent if that plays any role. So the substrate here, of course, is a tertiary substrate, right? And so that should be leading us towards probably SN1. That's what the tertiary substrate gives us as a potential mechanism. The leaving group here looks like it's OH, and we know that that's a very poor leaving group, so we need to somehow turn this poor leaving group into a better leaving group. The nucleophile, this is the evidence we have that helps us decide on the nucleophile. Probably going to be OCH3, maybe with an H there. We'll think about that. And the solvent, well, the product here has chirality center, but we're indicating that we have both enantiomers here. So that again is leading us to an SN1 type mechanism, and so the solvent should be protic polar. Polar sort of unnecessary there. Any solvent that's protic will be polar. So the solvent needs to be polar protic. Perhaps the solvent is methanol. Maybe we do this, and that's our solvent. I don't think that's the full answer, though, because we still have this poor leaving group. We need to turn that leaving group into a better leaving group, and we can do that and achieve SN1 type mechanism with H2SO4. Basically, we protonate the leaving group, it leaves, then we can add our nucleophile. So if we just run down a quick mechanism, protonate the leaving group, I'll do a fake arrow right there. It'll look something like this. Now we have water as our good leaving group, and it's a cation, and we can do the loss of leaving group. That gets us to this tertiary cation plus water. And now I can use the lone pair on my nucleophile and solvent. And since it's the solvent, there is plenty of solvent molecules around. So this should be a very quick nucleophilic attack step. I'm not going to specify stereochemistry anymore because we know that both versions will be formed, R and S. So we'll be sure to specify that in the end product. And of course, attached to this oxygen comes along the methyl group and the hydrogen. And then I need to use another molecule of solvent to remove the extra hydrogen. I could use the conjugate base of sulfuric acid, but it's not a very good base. And that's because sulfuric acid is an extremely good acid. So it's more likely that the methanol solvent acts as the base in this case. And so now I have the product, which I had already drawn here. But you can see how this mechanism proceeds. It requires a proton transfer step to start and to finish this reaction. So we have 2 additional steps in addition to our normal loss of leaving group and nucleophilic attack step. Let's look at the second reaction on this page. We have a secondary substrate and we have a secondary product, and we notice that it does indicate inversion. And so that might lead us to think about SN2 mechanisms, which are possible with secondary substrates. We have a poor leaving group again, just like we did before. So we need to somehow convert that into a better leaving group. And our nucleophile, hopefully you've identified that as probably Cl-. And in the solvent, we want to support SN2 with our solvent. So DMF, DMSO would be good. The question becomes then, how do I convert this poor leaving group into a better one? And if I use the same strategy as above, I'm going to get a cation formation. And that could lead to not inversion, but racemization, and potentially we could rearrange, because this hydrogen could migrate over and create a tertiary cation. So I don't want to use acid here. And in most SN2 reactions, acid is not a good thing. So if we don't use acid, we will prevent racemization. So what's another way to convert OH into a good leaving group? Well, remember that that's tosyl chloride and pyridine. And that will get us, I'll draw it over here. Essentially, it turns our OH into OTS, and this is a good leaving group. And you'll remember that it's because it's highly resonance stabilized. You can look up the structure of OTS in your textbook. This is highly resonance stabilized, so it makes a great leaving group. So that's our first step, tosyl chloride and pyridine. The second step then is to add the nucleophile and some solvent that promotes SN2 chemistry. And so the chloride then can, I can draw it right over here, Cl-. We can do an SN2 backside attack, and that will produce, actually right over here, I don't need to redraw that, that will produce this product. So here we have a two-step sequence where we need to turn this poor leaving group into a better leaving group, avoiding cations. We don't want any cations here because that will rearrange our molecule. And so to prevent cations from forming, we want to turn OH into a better leaving group without acid. That's tosyl chloride and pyridine. Alright, here's another example. And again, we can evaluate this using the same techniques we've used. This is a secondary substrate. The leaving group is a good leaving group. It's Cl-. So we don't need to worry about making it better or letting it leave. And we have inversion over here. So that's probably going to lead us again to SN2 type of a mechanism. And our nucleophile is evident from the product. That should be I-. So I could use NaI as my source of I-. And if I want to support SN2 chemistry, I should use some polar aprotic solvent, acetone, DMSO, DMF, really whatever you want. And we'll write that under the arrow, as is common for putting solvents. And that's really it. That's all we have to do. There's no proton transfer required because I have a good leaving group. I don't have an OH. And my nucleophile is I-. It is not neutral, so it's not going to need to proton transfer anything at the end of the day either. So this is a pretty straightforward SN2 type mechanism. Okay, the fourth one here. Our leaving group is on a secondary carbon. It is, again, a poor leaving group. And we can observe that the nucleophile has been added to a tertiary carbon, and it's moved over too. So we're probably going to expect some sort of rearrangement. And our nucleophile should be some version of this O-ethyl, potentially ethoxide, or maybe ethanol. And because we see the rearrangement happening, that tells us that we need to set up SN1 type conditions. And so if we use ethanol as the solvent and the nucleophile, that gives us a polar protic solvent. And we know that we don't need really strong nucleophiles in an SN1 type mechanism. So let's use ethanol as the solvent and the nucleophile. And then we need to turn our poor leaving group into a better leaving group, and our goal is to form cations now, so no reason we can't use H2SO4 if I spell it right. And I'll even draw it out so that we can draw a proper arrow push. So there's H2SO4 drawn with the OH bond. So now I can do a proton transfer at the beginning of my mechanism. And if you want to be accurate, this is reversible. And now I have basically water as my leaving group, which is a very fine leaving group. So I could lose water. Try to draw my pentagon a little better this time. Now I have a secondary cation, and we need to evaluate it for potential rearrangements. And if I take one of these methyls and migrate it, I can form a tertiary cation. And we observed that necessity already because there's a methyl where the leaving group used to be, and there's one methyl left on this upper right carbon. So there's the new methyl in its new position, I should say. There's my new cation, that's tertiary. And now I'm ready to add my nucleophile. The nucleophile can only be, in this case, the solvent. So that's going to add like this. Of course, we're going to get racemic mixture. And, of course, the oxygen brings along everything that it's attached to. So we still have this extra hydrogen. And the last step, then, is a proton transfer step. I would like to see you use ethanol as the base in this case, because the only other option we have is the conjugate base of sulfuric acid, and that's going to be too weak of a base. So let's use ethanol. Remember, there's plenty of solvent here. And we're going to remove that H and neutralize the oxygen, and that gets us right to our desired product. So in this case, we evaluated the requirement to turn this leaving group into a better leaving group, and we observed the fact that there's going to be a rearrangement happening, and that told us we can make cations, and we can use polar protic solvents, and we can expect SN1 type chemistry. So we can learn all that just by observing the changes that have happened as we go from our reactant to our product.